Welcome! Today, we're exploring the fascinating world of infrasound monitoring and how it helps us keep an eye on objects entering Earth's atmosphere. So, what is infrasound? It's sound waves with frequencies below the range of human hearing, typically under 20 Hz. These super low-frequency waves are generated by really powerful events. Think volcanic eruptions, large explosions, and significantly for our topic, meteors entering the atmosphere, often called bolides, as well as artificial objects like spacecraft or space debris re-entering. How does this monitoring work for these re-entry events? When an object enters our atmosphere at hypersonic speeds, much faster than sound, it creates intense shock waves. As these shock waves travel, they eventually transform into infrasound waves. The amazing thing is these infrasound waves can travel thousands of kilometers through the atmosphere with very little energy loss. This allows global networks like the International Monitoring System, originally set up to detect nuclear tests, to pick up these signals. This network has around 60 infrasound stations spread across the globe. Each station uses an array of highly sensitive pressure sensors called microbarometers. By using an array, scientists can figure out not just when the sound arrived and how strong it was, but also the direction it came from and its speed. When multiple stations detect the same event, the data can be combined to pinpoint the source location high up in the atmosphere through triangulation. This technology has crucial applications. Firstly, in planetary defense. When large meteoroids or bolides enter the atmosphere and break apart or explode, they generate significant infrasound. These networks provide a global, passive way to monitor these natural events. Analyzing the data helps determine the event's timing, location, altitude, and energy release. This is vital for understanding how often objects hit Earth and assessing any potential hazard. Secondly, it's increasingly important for tracking artificial objects. With more satellites and rockets being launched, the re-entry of space debris, old satellites, rocket parts, is a growing concern. Infrasound can help detect and track these re-entries, giving us valuable data to estimate their paths and potential impact areas. Planned re-entries like sample return capsules from missions such as OSIRIS-REx or Hayabusa are also monitored. Because we know their trajectories precisely beforehand, observing their infrasound signatures helps scientists calibrate their systems and refine their models. Recent research has focused on improving how we interpret this data, especially for objects that are moving sources, not stationary explosions. Scientists have found that the object's trajectory significantly affects the signals received, particularly for objects entering at shallow angles, less than 60 degrees from the horizontal. Specialized computer models are being developed to better analyze these long paths. Interestingly, objects entering at steeper angles above 60 degrees are generally easier to locate accurately because the sound seems to come from a more concentrated point. Researchers are also exploring complementary technologies. High-altitude balloons carrying infrasound sensors have shown promise, successfully capturing clear signals during the OSIRIS-REx re-entry. Fiber optic cables are even being tested for acoustic sensing. However, challenges remain. It can be difficult to distinguish faint re-entry signals from background noise. Accurately determining the trajectory, location, and energy also requires complex analysis, factoring in atmospheric conditions like wind and temperature, which affect sound travel. Improving the detection of smaller objects is another ongoing goal. Future work will focus on refining analysis techniques, combining data from different types of sensors, improving location and energy estimates, and potentially expanding monitoring networks with new technologies. In conclusion, infrasound monitoring networks are an indispensable tool. They provide critical information for planetary defense against natural impactors and for space situational awareness regarding artificial debris. By capturing these silent sounds from the upper atmosphere, we gain significant insights into the dynamic events happening high above our planet. The continuous improvement of these systems highlights their growing importance in monitoring near-Earth space. Thanks for listening.